Awesome. Well, thanks everyone for coming, and thanks, Matt, for your presentation. We're really looking forward to it. I'll just go through and give a quick introduction to our site. If our website you've got here, it has links to our seminar, upcoming seminar series. Matt has graciously let us kind of record this, so we'll put this onto our YouTube channel for those to you who aren't able to make it live. If you go to our seminar webpage, these names will actually become URL links that'll bring you to our YouTube channel where you can then watch them again. And if you haven't already, please sign up for our mailing list. We'll post kind of announcements to these seminars, and if there are any ongoing collaborations and workshops in the upcoming summer, you'll hear about those there. And then if you have any suggestions for speakers or have any questions that you'd like to get brought up and discussed within this seminar series, you'll feel free to contact us through the website there. Cool. Yeah, so speaking of that, GeoDAWG is going to be hosting a session at the 2025 YASPE session. It's J04, titled Data Assimilation and Machine Learning Challenges and Leveraging New Opportunities. So if you're interested in getting involved, please reach out to us, and we'll make sure everything is getting set up there. And today I'll let Anthony introduce our seminar speaker, and he'll control questions after.
Sure. Yeah. So today we are joined by Matt Lang, a research scientist, part of the British Antarctic Survey, with a background of implementing data assimilation into quite a variety of space physics models, from the solar wind, the atmosphere, and radiation belts, which we'll hear about from today, as well as machine learning techniques and their applications to space weather. So thank you, Matt, for joining us today. And feel free to share your screen and get started.
Yep. Can you share? Let's see if this works. I'm betting it won't. Big. Is that working?
Yep, looks good.
Cool. So yeah, Matthew Lang, and there's Anthony. Or was it Adam? I forget which one. Anthony. Was it Anthony who said it? Anyway, doesn't matter. I'm nervous. I'm primarily a data assimilator who applies data assimilation to space physics models. And in my current position, I've been working on applying data assimilation into the BAS Radiation Belt Model with Sarah Glauert and Richard Horn, British Antarctic Survey. So this presentation will basically, I'll start out by doing a quick introduction to radiation belts and BAS RBM, and then go on to talk about background of data assimilation and then how I'm incorporating it into BAS RBM, along with some ensemble experiments I've been doing to try and estimate uncertainty, and then show some preliminary results, because this only just gotten working, and the challenges I've come across. So the BAS radiation, the radiation belts in general, so they're a region of magnetically trapped particles around the Earth, comprised of an inner belt, which has a pretty constant electron population, and the outer belt, which is what I'll be focusing on, which has a far more dynamic electron population, which is driven more by the solar wind conditions, and it's where the satellites, geostationary and GPS satellites, tend to orbit through. So it's important that we model this accurately, because these satellites can be damaged through charging, etc., by enhancements in the radiation belt. So to model the Earth's radiation belt, we look at how the phase-space density of electrons changes in the radiation belts. And we do this through a Fokker-Planck diffusion equation, which models some physical processes such as radial diffusion across the magnetic field and wave particle interactions. And here's a nice little demonstration of the BAS RBM. Oh, sorry. And you can see when an enhancement occurs, it gets brighter and it encompasses this geostationary orbit, this satellite. So this is why we're interested in understanding the radiation belts, especially the outer radiation belt, to protect these geostationary satellites. So, as I said, the BAS RBM models through this 3D Fokker-Planck equation, which I think looks horrible. But it's basically saying the rate of change of the phase space density, F, is equal to the sum of these four terms. And each of these terms represents quantity. So the first term is the diffusion in pitch angle. So pitch angle, for those that don't know, is the angle of the particle's motion against the magnetic field. So it's looking at the diffusion in pitch angle is how that is changed over time. Then we've got, and that is primarily, the diffusion in pitch angle is primarily due to wave particle interactions and collisions. And then we've got the diffusion in energy, so the kinetic energy of the particle. And that's primarily influenced by wave particle interactions. So if you have a resonant wave, it can interact with the particle, accelerating it, increasing its energy. And then we've got radial diffusion. So this L quantity is the radius away from the center of the Earth. The magnetic field crosses the equator, assuming a dipole. And this radial diffusion term shows the diffusion of particles in and out, or well, radially in the radiation belts. And then finally, we have this loss term, which is the loss of particles to the Earth's atmosphere. So when they precipitate out, or when they escape out into the magnetosphere. And then another set of terms are these diffusion coefficients. So these are all pre-computed using, so the alpha and the energy ones, they're pre-computed using the PADI code. I'm not sure about the DLL, but these diffusion coefficients each contain information on, the physical processes that are happening and driving the diffusion in pitch angle, energy, and L star. And these are all, the ones that I'll be using are all purely dependent upon KP. Yeah. And so for BAS RBM, we have several inputs that we need to specify. So we need to specify an initial condition. That's phase space density. at all pitch angles, energies, and L stars. And then we need to specify boundary conditions. So there are 6 of these, 1 at each maximum, minimum pitch angle, maximum and minimum energy, and maximum, minimum L star. So these are the things that we need to specify. So the initial conditions, for example, can come from a previous model run. And then the boundary conditions, first off, we can specify 3 of them straight away. So the maximum and minimum pitch angles can be constrained by assuming that the phase space density doesn't change at either boundary, so it's flat. And then the maximum energy, the phase space density can be set to 0. Basically, we assume there's no particles at the highest energy. So that just leaves us with 3 boundaries that we need to specify. And for the case of BAS RBM, at least in the experiments that I'll be showing, we specify these by, firstly for the lower L star, so the inner boundary radially. We use a Ceres profile averaged at the lower L star, and then dependent upon what the KP is, we use that to calculate the phase space density at the lower L star at the energies required. For the L max, we calculate that at the equatorial, the 90-degree equatorial pitch angle by fitting a kappa function to the GeoDAWG data. So we get the GeoDAWG, we fit this kappa function to it, and then we translate those fluxes or phase space density out to the maximum L star values, assuming constant mu and J. J. And then we use a pitch angle distribution spread. And then the minimum energy is then calculated at the maximum L star. And then, this should be calculate the flux or phase space density at the minimum energy at the outer boundary, and then use the Ceres profile to calculate the minimum energy at all required L stars. So we have the structure of the Ceres profile, but using the flux at the that we calculated at the Lmax on the EMIN. So those are the main inputs that we have into BAS RBM. So I'll talk about data assimilation, what it is and why we use it. So data assimilation is sort of comes about from, if we have models and we have observations, what should we be believing? So for an example, if you have some model that gives you a forecast of the temperature of the room you're currently in, maybe you have a radiator here that makes it warmer, and a cold spot here for whatever reason. So yeah, our forecast, our model says, okay, it's going to be about 17 degrees Celsius here. But if I have a thermometer and take a measurement at 21 degrees, which should we believe? What does that observation tell us about our model? And what does the model or forecast tell us about the structure of the temperature in the room we're currently in? And what information can we get from both, and how do we combine those two pieces of information? And that's what data assimilation aims to answer. So the first question is, why don't we just use models? Well, a model is all well and good if you have perfect initial conditions, perfect physics, and there is literally nothing wrong with your model in the slightest, no approximations, which is never true. All models are wrong, but some are useful, as they say. So there's the famous butterfly effect, where you have a small perturbation away from an initial condition, made popular by the Lorentz 63 model. So depending on where you start on the attractor, if you have a slight deviation in initial condition, it can massively impact where you end up. So if you get them slightly wrong, you're going to have wildly differing forecasts from the true state. And the same with, if you have approximations, you further move away from the truth. And the same with errors in the physics, so an incorrect parameterization for example. So if we don't have everything perfect, then we can't necessarily trust that the model is producing the correct results. So then the obvious question is, why don't we just use the observations? Well, quite simply, they're not always where we want them to be. They're sparse. I mean, for the radiation belts, we only have a handful of satellites that can measure electron flux directly for, an area of 16 Earth radii squared, say. It's, not enough to fully constrain or model the radiation belts. And these observations, weirdly, aren't neatly arranged on an alpha energy L-star grid. There are gaps, delays, problems in data coverage for a variety of reasons, defense, failures of satellites. And then we have remote observations, which can provide a more global, large-scale picture, but don't necessarily have the information that we want. So we have VLF receivers, which gives us information about waves in the radiation belts, but doesn't give us anything about the electron flux directly, and magnetometers, which tell us what the Earth's magnetic field are doing. So there is information about the radiation belts in those observations, but not directly what we need or want. So data assimilation aims to optimally combine the models with observations to better estimate the true state of the system, for better forecasting and better estimation of what's going on. So an example I always like to show is this one of ozone forecasts for the ozone hole over Antarctica. So this is our model output. We can see we've got the ozone hole here. And then we've got our observations, which, as I've said before, aren't neatly arranged on a grid, but rather we have lines of them and massive spatial gaps in coverage. But by combining the two through data assimilation, we get an improved structure in the ozone and the ozone hole, and a better estimate of what the true ozone should be and its associated uncertainty. So how do we combine observations with models? I mean, simply put, we use Bayes' theorem, which states that the probability of some state occurring, so a state could be the ozone around the globe at every single grid point, or in the radiation belts case, it's the electron flux at every pitch angle, energy, and L star. So the probability of any state given the observations is proportional to the probability of the observations occurring given a particular state. So if we have a temperature of 21 at that point, at some point, and given our model, what's the probability of that observation occurring given our model output? And then we have the prior, which is the probability of a particular state occurring. So what's the probability that that particular structure of temperature in your room is true? And then a normalizing factor. So if we have this full posterior distribution, we can fully represent what the state is given the observations that we have, along with any uncertainties present within the system. So that's the ultimate goal. So to represent that, we need to use a histogram to bid everything and visualize it, because chances are we can't get an analytical solution. But the problem with this is, as we move to higher and higher dimensions, the number of bins we need increases. So a one-dimensional system split into 5 bins only needs 5 numbers to be stored. But 2D, 5 equal bins in each dimension, we need 25 numbers, and so on and so forth. 3 dimension, 125, 4 dimensions, 625, etc. So an n-dimensional histogram requires the number of bins to the power of n numbers to be stored. And for comparison, a 1D radial diffusion in BAS RBM, that's a 48-dimensional system. So that's the electron flux at every L star, 48. So that's for 5 bins, that's something like, I think it's 3 of the order of 10 to the 33 numbers that need to be stored. And the full BAS RBM system is around 50,000 dimensions. So even with 5 bins over each dimension, it's just too many numbers that need to be stored, and it's impossible to do. So we have to make approximations. So the common approximations used are assuming everything is Gaussian and that the numerical model itself is linear. This is never true. Almost never true anyway. If the model is linear and everything is Gaussian, then it will stay Gaussian as the model propagates things forwards in time. But the advantage of assuming this is that if everything is Gaussian, we only need two values to fully define the distribution, the mean and the covariance matrix. So that's why we make this assumption. And then we need to look at what do we mean by an optimal form of the posterior distribution. So if everything's linear Gaussian, the maximal posterior probability and the mean are identical. But if we have, for example, a bimodal posterior, it's not clear what's optimal. So in this example, we have two modes. So two areas of maximal probability for two states. Which would you choose? I mean, one may be unphysical, so that automatically makes it easier. But then we have the mean in the middle of these two, but that occurs at an area of low probability. So is that really the best value to be taking? So it's unclear what is optimal. And so there are three main groups of data assimilation that are formed. So we have variational methods, which search for the mode, sequential, which search for the mean, and then particle filters, which aim to recreate the full posterior distribution with an ensemble. And then there's hybrid methods, which combine different features from each group. So the variational methods, the main one is 4D-VAR, so-called gold standard that's used in operational weather forecasting, primarily because it's fast and efficient, even for high-dimensional systems. However, to get this fast, efficient thing, we need to generate an adjoint model. So an adjoint is the transpose of the linearized model. So that's difficult to compute and specific to a model, a specific version of a model. So if you update the model, you have to update your adjoint. So you have to have some support for an adjoint going forwards. Generating the adjoint sort of rules out 4D-VAR for BAS RBM, primarily because it's quite a large model, and it would take a long time to compute efficiently, and it would only be specific to a specific version of the model. So that sort of rules it out for BAS RBM. So we look towards the sequential methods. So the primary one is the Kalman filter. So for when everything's linear Gaussian, brilliant, it's equivalent to 4D-VAR. But it requires that we explicitly evolve and store error covariance matrices, which means we have to store the dimension squared numbers. So that makes it impossible for high dimensional systems. So after that, there's the ensemble Kalman filters and smoothers, where the error covariances are instead estimated by an ensemble of model runs. So we get rid of having to explicitly evolve the full error covariance matrices. So we can use the ensemble Kalman filters for higher dimensional systems. But we do need enough ensemble members to accurately estimate the error covariance matrices. Too few when we don't have, there are spurious correlations that can be introduced, and it may underestimate the total covariance because we're only looking in however many ensemble members' directions, which is typically less than the dimension. And then the particle filters, which, as I said, approximate the full posterior covariance matrix with an ensemble of particles with no assumptions of linearity or Gaussianity. But it is prone to ensemble collapse, where everything, all the weight and information collapses onto a single particle. And as we get to higher dimensions, the number of particles we need to avoid this increases exponentially. So this rules out particle filters for the BAS RBM. And sort of leaves us with the ensemble Kalman filters. And so this is what I decided would be the most appropriate scheme for BAS RBM, primarily because it's easier to implement into the mature model with minimal changes to BAS RBM, and it does have some precedent. It has been used, the ensemble Kalman filters have been used in previous studies, and also that portability between different versions of BAS RBM is constantly being updated, so it's important that the data simulation should be able to move with it. And it can be efficiently implemented with MPI, so doing parallel processing. So we send the ensemble members to different processors, and we can run it much quicker. So yeah, and I've got a few slides just briefly talking about what an ensemble Kalman filter does, although I suspect everyone knows. So for BAS RBM, we initialize an ensemble of flux values at all points on the model grid. So that's electron flux at every L star energy pitch angle in these crosses, and transform it into a one-dimensional vector, and do that for every ensemble member. Then we run these ensemble members forward to the observation time step, where we have an observation with some uncertainty. And then we use our ensemble members to estimate the error covariance matrix, so the uncertainty in our prior state. And then we use the Kalman filter equations to update each ensemble member and get an estimate for the posterior uncertainty. And then we repeat that until everything's been assimilated. So this leaves us with a whole amount of work we need to do, looking at generating ensembles for BAS RBM. So we need to look at what's uncertain in BAS RBM's inputs to generate an ensemble that's fully representative of the uncertainties present within our model simulations. So there are, three main areas. We have our initial conditions, We know they're pretty uncertain. Oh, I mean, they could just be generated from IRASA data or from a previous model run. There's definitely some uncertainty there. In our boundary conditions, there's also a large amount of uncertainty. I mean, two of them are based on averaged series profiles. And the Lmax outer boundary is based upon GeoDAWG data, but typically with BAS RBM, the Lmax is something like L star of 7, whereas the GeoDAWG data is much closer in. So we're translating it out, assuming everything the same mu j, but that translation may not be true. We may have errors there, even though we're basing it off the GeoDAWGs. So yeah, we have these sources of uncertainty, and we can group these into different groups. We have our initial conditions, as I said, and then we have the Emin and L star max boundaries, which are dependent upon the GeoDAWG data or are fits to the GeoDAWG data. And then we've got the lower L star boundary and the diffusion coefficients, which are dependent upon Kp. So by perturbing the initial conditions, Kp and GeoDAWGs, we can sort of simulate some of the uncertainty that's present within our simulations of BAS RBM. So yeah, this is what we're proposing. So there are a few ways to do this. For perturbing the initial conditions, we can just generate an initial condition and then perturb that directly just by adding a random variable. Or we can produce an ensemble in the prior run to produce spread and produce uncertainty for an initial condition. For the GeoDAWGs, again, we can directly perturb them, or we can perturb the GeoDAWGs data that's input into the kappa fits, or we can take the GeoDAWGs data, generate a kappa fit, and then perturb the kappa parameters. And then for Kp, again, we could just do a Gaussian perturbation, or which may not be the best thing. For example, if you have Kp at 9, you're not expecting a Gaussian distribution for when it's bounded upwards. You're not getting higher than 9. And also, you're expecting it to fall quite a bit and not stick around 9. So a simple perturbation probably isn't the way to go. Or what we've done is perturb Kp based upon a distribution based upon historical Kp. So, sorry, I had one more slide before that. These are the things that I'm going to be doing in the experiments that I will show, just doing direct perturbation of the initial condition. I have tried doing these two for GeoDAWGs data, but perturbing the GeoDAWGs data didn't seem to change too much. But perturbing the kappa parameters led to a positive bias being introduced into the simulations. So we think that when the kappa parameters were, when the outer boundary was increased, then that was being radially diffused into the model domain, and that wasn't balanced when it reduced again. So we were getting this biased flux in our being radially diffused in. So at the moment, so these are still work in progress. At the moment, for these experiments, I'm just directly perturbing. And then, yeah, I'm perturbing KP based upon historical KP. And the way I'm doing that is by taking for each KP value, I look at what the KP is in 3 hours' time. And then I can make up histograms or probability distributions for KP in 3 hours' time based upon what the current KP is. So for KP equals 1, for example, this was the distribution histogram I got out. So there's a very low chance of it going above 4. Whereas for when KP was 5, it was far more, any KP value was possible in 3 hours' time. And it was far more Gaussian than KP9, which is far more skewed, as I mentioned, albeit not as far. You're still getting high KP in 3 hours' time. And so this means that we can, based upon what the KP is at the moment, we can draw a random KP from these histograms in 3 hours' time. And so from that, we can generate an ensemble, albeit not for the first 3 hours. And so here's an example of an KP ensemble with its full range. And yeah, we are introducing spread into the KP in a more, I guess, realistic manner based upon the historical data sets. Okay, so I've done some preliminary experiments using BAS RBM. So I've generated a data assimilation system for BAS RBM. And I've done some preliminary experiments. So firstly, I'm going to show some just ensemble experiments, which will be used as priors for when I do the data assimilation. So for these experiments, I've got 150 ensemble members run over a single day. It can be run for longer. It's just for the preliminary stage, I've just done it for 1 day. And any perturbations are applied to the logarithm of the flux. So I'm perturbing it to the order of the fluxes or phase space density. Yeah, so the ensemble generated by just perturbing the initial conditions. So I perturbed the logarithm of the initial conditions by an unbiased random variable with variance 1 at all grid points at this initial time. So, each of these are the mean omnidirectional flux at half an MeV, an MeV, and about 2 MeV. our L stars from 3 to 7. The dots are the Galileo data, which I will later be assimilating over the 1st of September 2018. And yeah, everything is omnidirectional flux. And then on the right, I have the standard deviation of the ensemble at these energies. So for these ensemble experiments, it's perhaps more instructive to look at the standard deviations and see how they change between the different ensembles. So if we perturb the initial conditions by an order of 1, then we can see that, yeah, we start with 1, but as we go through in time, since we've not perturbed the outer boundary and the certain outer boundary conditions are being radially diffused into the system, meaning that we're losing the spread in the ensemble at the outer L stars. And this is perhaps a bit worse at the higher energies. This low little band here is beneath the minimum L star for that energy. So you can sort of ignore that bit. It's not realistic. If we then look at perturbing the boundary conditions by, again, the same random variable distribution, but instead of doing it at the initial time, we're perturbing the Lmax boundary at all time steps by some random variable with variance 1. There's obviously no real change in the mean because it's an unbiased random variable that's being used. But you can see that we've sort of got the inverse of what we had with the initial conditions being perturbed. We have no spread at the lower L stars, but we have the high spread being radially diffused in to the system as time progresses. So yeah, that's what we see with the Lmax generating an ensemble by perturbing the outer boundary. And then from our KP, we have far less spread in our fluxes. This could be because we have it's low KP. We've not got a huge amount of activity in this current time frame. I need to check later what happens if we have higher KP. Do we get more spread in the ensemble? But you can see that we're getting some spread in this region here. I'd be interested to know more about what people think about why it's in that particular region. Maybe it's the rate of diffusion, radial diffusion, that's causing that. I'm not sure. So yeah, each one leads to a different part of the model domain being updated. The KP seems to be a lot lower at the moment, but yeah, I haven't looked conclusively at why that is. And then when we perturb everything, you can sort of see we have everything that we had before, but we have this area of lower standard deviation, which doesn't, in my mind, doesn't seem to make sense. Why would you have an area that's more certain compared, even when you've applied the same perturbations? Why would you have so I don't know, something doesn't quite seem right to me in the ensemble, in the spread there. But yeah, that's sort of what we get. And now, perhaps the more interesting bit, and what you're all here for, the data assimilation setup. So I've been using an ensemble transform Kalman filter. So the same as a ensemble Kalman filter, but transforming the state vector to make it more efficient and faster. And then same setup as before. And I'm assimilating the Galileo GSAT 0207 satellite at 1 MeV. And I've got an error covariance in the observations of 1 order of magnitude. I need to do some work to verify what the observation error covariances should be, and look into that more. But this was for this initial study. I've just perturbed it by just chosen an order of magnitude. And here's an example of some Galileo data looking all pretty for May 2024. And if you're interested, this is where the storm occurred. And you can see the dropout in flux. But the main things that we saw were a bit further in. So, yeah, anyway.
Hey.
Oh, hello.
Yeah, hey Matt, just want to give you a heads up. There's about 7 minutes left in the hour if you
Okay.
want to leave a little bit of time for questions.
Yes, I've got 4 slides left.
Perfect.
Well, yes. So I've used my data assimilation method and applied it to the ensembles that I just showed. So we have this. So the middle plot is the assimilated energy channel. And we can see that we have this high band in our flux, but once the Galileo data comes in and is assimilated, we have a sharpish reduction in that. And we're getting closer to what the observation says. And not just at the assimilated energy channel, but that's also happening at the other energy channels, despite them not being assimilated. However, we do have these weird patterns in the standard deviation. We need to conclusively double check what's causing these. We think it's because BAS RBM transforms between the energy pitch angle L star grid to a mu J L star grid and back again. The data assimilation is currently only performed on the on the pitch angle energy L star grid. So it could be that something is going wrong in the transfer between the two, but more work needs to be done on that. But perhaps the most important thing for this particular one is you can see that in this outer region, you can see there's this injection of high flux, which isn't being corrected by the data assimilation. And that is because we have no spread in the ensemble there, because it's been, radially that certain outer boundary has been radially diffused in. And so the DA is saying, okay, there's no spread there. The model must be perfect. So don't move towards the observations. So yeah. And then if we do the opposite and look at just perturbing the Lmax boundary, we can see that we get the inverse, basically. The area of no spread is now here, so we're getting no change. This high flux band isn't changing in response to the observations, but we are getting some change at the outer boundary. So that's good. However, at present, because the outer boundary is pre-specified, if we update the outer boundary at the next time step, it's reset to whatever it was. So it's been re-diffused back in. So I need to do something to permanently update the outer boundary based upon what the data simulation says. And then quickly, KP, there's very little spread, so not much is happening. And yeah, when we have everything in there, you can see that we're getting this reduction. We're getting it sort of at the outer boundary, and it's being controlled by the observations as they're assimilated, and it is going to other energy channels. And so, yeah, I'll just leave that there. That's my summary. Yeah, preliminary, at the moment, the data simulation is behaving as expected, but there are a few problems, but I need to do some more work on verification. Yeah, that's it from me. Any questions?
Cool, fantastic. Thank you very much, Matt. We're almost at the hour, but any questions from Matt?
There's one in the chat.
Yeah,
So
so
we can read it off too for when this is posted later. So what magnetic field models was used in the simulations?
yeah, so L star is used. So I used Urban with a Alton Pfizer quiet magnetic field model.
I have a question. So, we have one from Angelica. Go ahead.
Hi, can you hear me?
Yep, I can hear you.
Oh, wonderful. Matthew, thank you for this interesting talk. So I have a few questions. So first is, you are assimilating, the data you're assimilating is only one energy channel, but does it have pitch angle resolution, or it doesn't? You're
no.
only showing omniflux.
It's omnidirectional flux.
Okay. Because this might also be one reason why you're getting these results, because your grid actually is pitch angle resolved, right?
Yes, yes.
Mm. And then the other thing I wanted to ask, so how, what is your assimilation step, your time step for assimilating are you assimilating like equally to the model step, or is it different? Do you assimilate every time that you run the model, or do you have like a
it's every time we have Galileo observation. So there are time steps where we don't have that, where the Galileo is at higher L stars, or there's just missing data. So in these patches,
so basically you are what is the cadence of this data? I'm sorry, I don't know.
Okay.
this
So
really.
the data, let's see, I don't know the cadence off the top of my head. I think it's every 5 minutes, but the model is every 600. No, that's the output. Yeah. I can't remember the model step off the top of my head for some reason. I have 600 seconds in my head, but I think that's just what its output.
Okay.
Yeah, the cadence is 5 minutes.
Okay.
Yeah, but it's not always. It doesn't always exist, or L star doesn't exist, or Urban doesn't produce an L star for whatever reason. So it's not necessarily that.
Because what could also be happening is that your assimilation window is too small, and then maybe you have too little data in that time frame. So maybe sometimes, so what we do sometimes for our studies is that we increase the assimilation window so that we have a bigger portion of the grid that is covered by data. So
Yeah, I mean that is a possibility. These were just done for short time windows. Just as preliminary things, I need to look at it for longer windows.
yeah, this is something that you certainly should try. Yeah.
But what worries me is whether or not the spread will still be there after we assimilate, repeated orbits. Because you can already see that it's gone from, an order of 1 to about 0.3. So it's lost a third of the spread. So would we still be getting updates? I don't know. Yeah.
Yes.
It's something I need to look at. Yeah.
Okay, thank you very much.
Anyone else?
Any other questions before we wrap up for the day? Okay, well, if not, then thank you again very much, Matt, for sharing this with us today.
No problem. Thank you for having me.
Thank you very much.
Yes.
Everyone.
Thanks, Matt.
Okay, bye. Good to see you, everyone.
Bye.
Bye.